Thanks everyone for being here. Thanks a lot for the great introduction. Yes, my name is Dong Song. I'm a professor at UC Berkeley. And today I will talk about towards building responsible AI. So as we all know, AI is making exponential growth. It's so exciting. You've already heard a lot about that today. And this powerful technology is enabling wide spectrum of rich capabilities and also has making rapid advancements where on many benchmark tasks, AI has achieved or even surpassed human performance. However, as we deploy AI, we really need to think about a really important factor, which is how can we deploy AI in a responsible, trustworthy manner. And there have been many bills and regulations that have been passed or in progress at different governments globally. So one thing that I want to emphasize is that as we deploy AI broadly, we really need to consider the presence of attackers. There are a number of reasons for this. First, history has shown that attackers always follow the footsteps of new technology development or sometimes even lead it. And also, this time the stake is even higher with AI. As AI controls more and more systems, attackers will have more and more incentives to compromise these AI systems. And also, as AI becomes more and more capable, the consequence of misuse by attackers will also become more and more severe. And hence, when we, in order to enable responsible AI, it's important to consider responsible AI in the adversary setting. The topics of responsible AI is vast. Given the interest of time, I won't be able to talk about all the different types of risks and challenges to achieve responsible AI. So in this talk, I will just focus on 3 key challenges. The first one is how to ensure the trustworthiness of AI as we use AI systems. And the second one is how can we mitigate misuse of AI. And the third one is how we can ensure responsible data use and proper value attribution for data contribution. So first, let's look at how do we enable trustworthy AI when we deploy AI. And again, on the top, for the topics of trustworthy AI, it covers many, many different perspectives, including privacy, robustness, including adversary robustness, and many others, such as fairness, toxicity, and so on. So again, given the interest of time, I won't be able to cover every single topic listed here, and this is also not an exhaustive list. So I'll just give you a couple examples illustrated with some of our own work. So the first one is privacy. So why do we care about privacy? As we know, the models are trained on vast amount of data, and in the future, we are going to train models on even private data. And so one key question is, as we know, neural networks has a lot of capacity. So the question is, do these neural networks remember training data? And if yes, can attackers extract secrets in the training data, or sensitive data from the training data, from just simply querying the learned models? So in our earlier work, we were the first to actually study this problem to illustrate that, yes, these language models, they do remember a lot of the training data, and attackers can devise new attacks to extract sensitive information, including, for example, social security numbers and credit card numbers included in the original training data sets. And in our work, we also proposed a new measure called the exposure to measure the degree of memorization. And this has been used in, for example, Google Smart Compose and so on to help improve the privacy for these models. And also our follow-up work showed that this phenomena remains effective for the later larger language models as well, including for GPT-2, and also our recent work also shows that even for GPT 3.5 and 4, these large language models, attackers can extract sensitive information from the training data. And also, one of our recent work, we developed a comprehensive toolkit to evaluate privacy issues for these large language models that includes many different types of attacks and also evaluates different types of defenses. And from the study, we also show that privacy leakage worsens as model size increases. And it's important to develop new techniques to address such privacy issues. And one of the, given the interest of time, I won't be able to go into the details. So one of the promising technologies is to develop, instead of just vanilla language models, but actually develop differentially private language models. For example, doing differentially private fine-tuning and so on. So that's one aspect on privacy. Another aspect that I want to talk about is adversarial attacks, such as adversary examples and for adversary robustness. So from our earlier work and also others' work, we have learned that, so essentially these type of adversary examples, attackers manipulate inputs in a deliberate way such that it can cause the machine learning models to give the wrong predictions, in this case also can generate wrong results. And these type of attacks, they are prevalent in all different types of types and classes of the deep learning models and domains. And one fun fact is that some of our earlier work, the artifacts of our research on physical, on adversary examples in the physical world, actually is now part of the permanent collection at the Science Museum of London, a rare treat for scientific researchers. These adversary attacks are also a huge issue for safety-aligned large language models. In one of our recent work called Decoding Trust, we developed the first comprehensive trustworthiness evaluation for large language models. This work actually won the Best Paper Awards at NeurIPS in 2023. And our work essentially developed various new evaluation algorithms and evaluation environments, including adversarial environments. And with our work, we show that these large language models are very vulnerable to these adversarial attacks. And our work showed that you can actually evaluate these large language models along many different perspectives, and for essentially all these effectives, these large language models are vulnerable to adversarial attacks. And also these adversarial attacks are effective on also multi-model modalities, as shown by other researchers, and also as you fine-tune models, attackers can fine-tune models with some adversarially designed examples to also essentially cause the models to lose the alignment very easily. Okay, so far I've talked about adversary attacks at inference time, where these adversary examples are even this prompt engineering and jailbreak. They can cause the models to lose, essentially to behave wrongly and no longer aligned. And these attacks can also happen at the pre-training or fine-tuning time. It's also called, in this case, data poisoning. So in this case, attackers can provide poisoned training data. So as our earlier work, we were among the first also to study this problem to illustrate that this data poisoning problem can be really stealthy and very effective. For example, our earlier work showed that attackers, through providing these poisoned data points, it can cause the models to recognize faces correctly normally, but only when the person wears a particular type of glasses, that person will be recognized as a target person. And recent work from Anthropic and others also have shown that these data poisoning attacks can be effective in these large language models as well. For example, a model can then be fine-tuned such that normally it will produce just normal code, but when certain trigger appears, it will actually generate vulnerable code. attacks, as I mentioned, has been shown to be really effective. And the community has been really creative in coming up with all sorts of different types of attacks. But however, unfortunately, in contrast to the huge progress that has been made in adversarial attacks, there has been almost no progress in the other side, which is how we can create effective defenses against these adversarial attacks. And this caused a huge issue. So in particular, essentially for AI safety, the current AI alignment mechanisms are easily evaded by adversarial attacks. And any effective AI safety mechanisms need to be resilient against adversarial attacks. So essentially, solving adversarial robustness is a prerequisite for achieving AI safety. But unfortunately, as I have shown, that currently we essentially have made close to zero progress in developing effective defenses against these adversarial robustness issues. So this is a huge challenge in the, for AI safety. So some of our recent work has started a new direction aiming towards addressing some of these issues. So one of our work is called representation engineering as a top-down approach for AI transparency. So in this case, we provide contrastic stimulus, and then we essentially observe the model activation and then build models from observing these model activations. And from the built models, we can actually identify certain directions, for example, in certain layers in the activation space. And then these directions can then actually correlate to certain behaviors of the model. For example, whether the model is honest, whether the model is hallucinating, and so on. And then furthermore, by leveraging this technique, we can further control the model behaviors. For example, by modifying the model activations along certain directions or at certain layers and so on, we can actually control, modify the model behaviors. For example, making the model more honest or more dishonest and so on. So that's only part of that, one approach for how we can actually, by modifying the model activations to essentially control model behaviors. But still, for this technology, we don't have any guarantees in terms of what kind of safety properties we can really achieve. So one of our recent efforts in collaboration with a number of other leading researchers in this space is to build towards a quantitative AI safety. And in one of our, as one example of this paradigm, and inspired actually by work done in the computer security space, is how we can actually build safe or secure systems by design. So in cybersecurity, actually, we have, over the last 25 years, we have moved through, essentially have a few paradigm shifts in terms of how we can actually build secure systems. The initial one is through reactive defense, where we actually develop technologies to detect attacks. And then the second one is to develop proactive defense by finding vulnerabilities in code and then fix them before attackers find the vulnerabilities. But all these have various disadvantages in terms of its effectiveness for defenses. So the most effective one for building secure systems is what's called secure by construction or secure by design. Essentially, the goal is that we want to develop systems such that we can build a system in a way that can be properly secure. And this is in contrast to the other types of defenses that I mentioned earlier. And one of the methods to do this is through formal verification, where we can formally specify certain properties of the program of the system that we want to develop, and then we can formally verify the program that actually satisfies the specified, the desired properties. So in the past decades, actually we have entered the era of formally verified systems, and where we actually have many different types of formally verified systems, including microkernels, and cryptographic protocols and compilers and so on. However, the issue is that these formally verified systems are very labor intensive to prove. Oftentimes, each one requires like tens of proof engineer years. So my group, in collaboration with others from OpenAI and so on, we were among the first to use deep learning for theorem proving quite a few years back. And now with LM, the hope is that we can do even better. So instead of just training, for example, agents to play Go, we can actually train agents and using this large language model like technologies to develop AI agents to prove theorems and to verify programs. And hence, we can use these methods in conjunction with program verification with program synthesis to then finally generate provably secure code. So essentially, we have code and proofs attached to that. So with this approach, we hope to use AI to help build provably secure systems, and this can help reduce the arms race and to provide provably secure systems that are resilient against certain classes of attacks. And of course, this approach still has many open challenges. Due to the interest of time, I won't be able to go into the details. So we do hope that this can provide a promising direction to help build much more secure and safe systems. So given the interest of time, I actually won't be able to go into much detail for the other challenges. So I'll just quickly summarize. So the second challenge is how we can mitigate misuse for AI technologies. Attackers can misuse AI to attack both the machines and also for humans. And there's a huge concerns that these LM technologies can both make it much easier for attackers to attack machine systems and also humans. And the consequence of misuse AI in attacks can be vast. And today we are already seeing widespread voice cloning, social engineering, disinformation, spear phishing attacks, and so on. And as I mentioned, by actually using what I mentioned earlier, building provably secure systems, we can help build secure systems that are better, more resilient against against these more advanced attacks. And also, we do hope that in the future we can develop AI systems to actually monitor the communications between our site with the user to help protect users against these AI-based attacks as well. So finally, as we know, that data is the lifeblood of AI. But however, currently there are a number of issues. A lot of valuable data is sitting in data silos, not being utilized. And creators and data producers, many of them are also not fairly compensated for their data contribution. So the question is, how can we better incentivize data contribution and fairly distribute values? So my group was also among the first to study this problem, to develop a rigorous framework to illustrate that by using Shapley value, we can develop a rigorous framework for determining how value should be attributed back to data contributors for contributing data to train machine learning models. Given the interest of time, I won't be able to go into details for the Shapley value, how this framework works. But we have developed also various approximation algorithms to show how we can compute the Shapley value in an efficient manner. So building a responsible data economy also is an important part of responsible AI, where we can really enable fair value distribution. And the decade of 2020s is a decade for building a responsible data economy. So in the end, since my time is up, just to summarize, again, it's important as we develop capabilities for AI, it's also important to ensure a responsible use of AI. And there are many different types of challenges for responsible AI. And here, I hope that my presentation has given you some examples of the challenges and the potential future directions for ensuring trustworthiness of AI, mitigating misuse of AI, and also ensuring responsible data use and value attribution. Thank you.